Hello students, my name is Pallavi and welcome to the channel of Parallax. Today we are going to discuss question number 6, 7 and 8 of paper number 0625, the extended paper of physics, that is 04. We have already discussed question number 1 to 5 in the previous two videos, the link of which you can see in the comment section. Let's begin with the question number 6. I hope the screen is visible to you. Here we go. Before beginning, we are going to use blue and black ink for all the answers which we have to write on the paper according to exam standards. And red ink would be for explaining the concepts to you all. Sometimes that's also important, isn't it? Okay, here we go. So the figure 6.1 shows a converging lens and its principal axis. The points F1 and F2 are each principal focus of the lens. So this is the lens which you see over here. And an object O is placed between F1 and the lens. Now you must be wondering how to make or how to create the image for this object, right? The thing is, you don't have to remember the position of the object and accordingly position of the images for IGCSE exam. Why do I say that? It's very easy to just remember 2 steps, and it's just those 2 steps which you have to do in every paper so that you get the image correctly. What are those 2 steps? So what you do is, the first step is you draw a ray from the object which is parallel to the principal axis. The black line which you see is the principal axis. And you draw a ray which is parallel. I hope this looks parallel enough, right? Or you can just make it like this. Okay, that's better, I guess. And never forget to put the direction of the ray. Now, the rule is, this is the first rule. Remember, there are 2 rules. So the rule is, when you make a ray which is parallel to the principal axis, after refraction from the converging lens, it will always pass through the principal focus. So any ray which is parallel to the principal axis will always pass through the principal focus after refraction. So this will be the path of the ray from here, head of the object, and parallel to the principal axis. Okay, so that was our first ray. All you need to do now is draw the second ray. The second ray has to be this. That is a ray which is passing through the optical center. That is exact center of the lens will pass without any refraction. So if you know only these two rules about refraction and lenses, you will be able to do any question which comes in your exam regarding tracing of creating images or figuring out where the image would be, etc., etc. Now have a look at this. These 2 rays they appear to diverge, right? They actually diverge, not appear to. They are diverging after the refraction from the lens, from the convex lens. So what do? So we extend them backwards. So I'll use a lighter shade to show this, because the rays are not actually being extended over here, or the rays are not coming from this point. However, they appear to join at this point, right? Remember, they are starting from the head of the object. So they have diverged after passing through the lens. But we are drawing a straight line and we want to see where those 2 rays start from. Where is the point where they start from? What is that point? So that appears to be over here. And therefore, the rays are not actually meeting at this point. So this kind of image forms. So wherever the rays meet or appear to meet, that's where you make the image. And this yellow line which you see over here, yellow arrow over here, this is your image. Clearly, it is a virtual image. Why do we call it a virtual image? Because the rays are not actually meeting. If the rays meet actually after refraction, then you will get a real image. That's the difference between virtual image and real image. So we are getting a virtual image over here of this. Let's name this I. This was O, right? So this I is the virtual image of the object O. it is enlarged, that is, it is magnified, it's bigger than the object O, and it is upright. That is, it's not inverted, right? It's exactly like the object and behind, formed behind the object. So let's have a look at the first question now. So the question says, on figure 6.1, draw two rays from the top of the object O to locate the image. This is what you have located. You already located the image. It's a virtual image. Label the image I. We have already done that. The object O is moved to the left along the principal axis so that it's further from the lens than F1. That means now your object will be further after F1, right? We'll try to draw that as well. The object is moved to the left, okay? Figure 6.2 is the diagram of the new arrangement. Let's look at figure 6.2. I hope the A part of the question number 6 was clear. Let's move on to the next part then. Okay, so this is 6.2 and underline 3 of the terms below and describe the image formed in 6.2. First, let's see whether this image is really being formed or not, okay? Let's check that. So, using the same logic which we used in the previous question. So, what do? Now, this you don't need to do in the exam. They have not asked you to draw the rays. If they ask, then you're supposed to draw the rays, okay? So, a ray which is parallel to the principal axis will always pass through the focus. And clearly, what we see over here is the ray is actually passing through the focus and meeting at the head, right? As you see, this is where the image is. And you draw another ray which passes through the optical center, which passes through the center of the lens. And we see these two rays now. Now look at the difference between the previous part and this part. What do you see? The two rays over here are actually meeting. Do you observe that? In the previous case, what happened? They were diverging after refraction. So we had to extend them backwards, right? But over here, they're actually meeting. Therefore, this type of image formed is a real image. So if you have to label 3 of the characteristics of the image, what would you do? It is a real image. What else do you see? It's an inverted image, right? And is it diminished? Is it enlarged? I think it's enlarged. It looks enlarged. It is not virtual and it is not same size, right? So these 3 would be the characteristics of the image, and that's where you get the 2 marks. I hope this was clear. The refraction, how the rays. So what we have learned over here basically is, when do you get a real image? When do you get a virtual image? Okay, the difference between the two. And what do you need to do to get a real or a virtual image? So you only need to draw 2 rays. First ray always is parallel to the principal axis. That means it will pass through the focus after refraction. Second ray will just pass through the center without any refraction. That's all you need to know. I hope this was clear. Just have a look at the diagram again. Now let's move on to the next question. Okay. Figure 6.3 shows yellow light passing through a glass prism. Now remember what happens in a prism. We have all learned that dispersion of light happens, right? However, over here, let's see what the question is asking. So this is a path of a yellow light. Before going ahead with blue light or whatever is asked in the question, let's have a look at the light which is Vibgyor. Okay, this constitutes white light, Vibgyor. So this is the order. Now you need to remember the order. Okay, order of what? See, from violet towards red, the wavelength is increasing. Okay, and the frequency of violet would be lowest as compared to red. But that's not the point here. Blue light or violet light scatters the most. That is, it bends the most when refracted. Red light does not bend that much, okay? Does not bend that much. In fact, that's the reason why traffic signals they have, or danger signs, they are made up of red light, because it will not get scattered. So it will have least bending effect. So you will be able to see the red light from a distance, right? That's the reason why red light is used for danger symbols as well as traffic lights, etc., etc. Okay, keeping that in mind. So we know that blue will scatter more as compared to yellow. Now it says Blue light enters the prism along the same path as yellow light. That means the path of yellow light, let's retrace it. So this is blue light now. Same path means this path is same as yellow. Let's draw the normal on the prism. So here we go. This looks like the normal, I hope. Yeah, it's a 90-degree, right? Okay. Now what happens to the refracted ray? Remember, whenever light travels from a rarer medium to a denser medium, it bends towards the normal, right? So this is our normal. Normal means perpendicular to the surface, okay? So it has to be 90 degrees over here. Angle of incidence is this angle. Okay. So this ray of light will bend more towards the normal. Let me make it a bit more in a better manner so that it's easy for us to draw the ray of light also. This looks more like a normal. Yeah. So the blue light will bend more than the red light, yellow light. Look, the yellow light has also bent towards the normal, if you see the black line. However, for showing the blue light, you will show it like this, maybe bending a little bit more towards the normal and then going over here. You draw the normal again on this side, right? You remember to join the points because it has to be not exactly accurate, but yeah, like this. And then it will scatter. So I had to use blue color. Let me use blue color so that there's no confusion over here. So we have blue color and here we go. So this is our path of blue light, and after refraction again, it will be scattering again away from the normal. So the blue light scatters away from the normal. If you see, this is the path of away. This would have been towards, this is away, right? So it scatters away from the normal, therefore diverging more. So that would be the path of blue light as compared to the black line, black arrow, which you see, which is originally the yellow light. I hope this was clear. And this is 2 marks of your question. Moving on, let's move on to the next question. Okay, state a typical value of speed of sound in air. This you need to know. It's 330 meters per second. The accepted range is 330 to 350. The masking accepts that much. However, 330 is fine. Okay, if you answer it as 330 meters per second, that's more than enough. Okay. Sound wave has, a sound wave in air has wavelength of 22 millimeters. Using your value of this speed in sound in A, calculate the frequency. I have written down the answer so that we can match it when we do the question over here in this class. So sound waves wavelength is given. Now I'm going to use the formula, but I'll tell you how an idea of remembering the formula as well. Okay, maybe that will help you. So let's first use the formula. So we know that lambda, or let's talk about, in fact, let's derive the formula. Okay, so we know that distance is equal to speed over time. How do you know that? Because distance is speed into time. So my bad. Speed is distance over time. So speed is distance over time. How do we know that? Because we know everywhere the speed is mentioned or the unit used is meter per second, right? That's how we remember distance by time is speed. You don't have to remember any formula. You just need to know that a car is traveling at, let's say, 20 kilometer per hour. So we know the speed of the car is 20. Kilometer per hour means distance by time, right? Okay. So speed is distance by time. Therefore, distance would be speed into time. Time is given by frequency, one by frequency. So it's reciprocal of frequency. Now applying this over here. Instead of distance, remember distance is measured in meters. You can have wavelength of sound because that is also measured in meters. And it's not just sound, it can be any other wavelength of any other electromagnetic wave. Okay. So lambda, which is the wavelength, is equal, instead of speed, we'll put v, which is velocity of sound or any other electromagnetic wave, times, instead of t, we can put 1 by f. That's the formula to be used. This can also be written like this: V is equal to F lambda. So personally, I never remember formulae. This is how I always derive in case I need to calculate any of these. Now, what do? We have to solve, right? So we know that the wavelength, so lambda into F is V, and you have to find F. So F would make F the subject. So F would be V by lambda. V over here is 330 and lambda is 22 millimeters. So 22 into 10 to the power minus 3. Let's check that out in the calculator if we are getting the same answer. So let me show you the calculator screen as well. Can you see the, yes, I hope you're able to see the calculator. So we are going to do 330 divided by 22. We get 15 and 15 and you have a 10 to the power minus 3 in the denominator. So you will get 15,000, right? So this was 15 into 10 to the power 3. Unit of frequency is hertz. Never forget to write down the unit. And that's how you get the 2 marks here. Moving on to the next part. It is a 4-marker. So that means you have to be very elaborate in the explanation and the examiner should be able to understand what you're telling and he should be able to understand that you know the concept well over here. Let's read the question first. Figure 7.1 shows a solid block made of hot liquid metal. As the liquid cooled, a bubble formed inside the block. The bubble is not visible from outside of the block, right? So what are we supposed to do here? Describe and explain how to use ultrasound to determine the size and position of the bubble inside the metal block. You may draw on the diagram. So how will you draw on the diagram? And what is the concept behind it? So this is what you do. Now see, you have to know the speed of the ultrasound inside the metal block. That is what you should know. So these are some of the points which you should know. Speed of the sound in metal. Okay. Another principle over here is ultrasound will either get blocked or, it will retrace back. That is, it will get reflected when it hits the air bubble or it will get absorbed. So it will get blocked altogether. So it will not pass through the air bubble. That is the second thing which you should be aware of when using ultrasounds. You should have a display. The display will tell you at what time the ultrasound came back and you will be able to record the time. So you know the speed in the metal, speed of sound in the metal, you know the time it took to hit back and therefore you can calculate how much distance the sound or ultrasound has traveled. So therefore you can locate the position of this bubble. I think diagram will help better to understand this concept. Let's say you are passing ultrasound like this through the metal, okay? So it passes through the whole body of the metal and you have placed detectors on this side, right? You have placed detectors. So the detector will be detecting the ultrasound and you know the length of the metal, that is, you know the distance the sound has traveled, or you know how much, so you can connect a transducer. The transducer will basically convert the sound signal into an electrical signal and place it on a, so you connect it to a screen where you can observe what's happening to the sound wave, right, as it travels. So you will be able to see how much distance the wave has traveled, okay, in the first case. In the second case, what can happen is when it reaches the air bubble, now either the sound will get stopped, which will not pass through, so the detector will not detect only any wave, right? Or it will go back to the emitter, okay? So it will go back. Then you know the speed of sound in metal, you know the time because you are connected to a screen, right? The signal will be visible and therefore, excuse me, and therefore you can look at the time it took to return back to the original emitter source. So you will be able to calculate the distance because, you know, speed of the sound is actually what? It's distance over time. So if you know the distance, that means you know the location of this air bubble. And like that, you keep doing the experiment. So you get the entire region of the air bubble, and therefore you know the exact position and size of the air bubble thus formed inside the metal block. That's how you use ultrasound. So the diagram can be like this. You don't need to draw the screen over here. You can just mention that transducer has to be used. You can just say that a display, so this is the display which we were talking about, a display has to be there so that you are able to track the time. And then you need to track the distance moved by using the formula of speed is equal to distance by time. Only one thing over here to be taken care of is that ultrasound will not pass through the bubble, so it will be reflected back. You need to mention that as well, although the mark scheme has not specified it, but that's how the examiner will know that you know the concept. Okay, I hope this made sense. Let's move on to the next question. This will be the last question we do today. Have a look at the diagram. This is the question on electricity, one of my favorite topics. So we have a circuit diagram given to you, and you have to calculate the combined resistance between Y and Z. Combined resistance between Y and Z. So what are the resistances which you see over here? We see that there are two of them, 8 and 4, connected in series, right? This is a series connection. So I'm not going to explain what a series connection actually is, but I'm going to explain what happens to current and voltage in series and parallel connection. Because I have seen that students, most of you all, forget whether current is in series, it stays same in series, or voltage stays same in series. What's going on? It's very confusing. I think I can agree with most of you, right? So I'm going to teach you or help you out here to, whenever you are forgetting what happens, what stays same and what changes, maybe this rule will help you. Okay. So before going there, let's just very quickly draw the diagram once more so that we know what we are supposed to find. So we are supposed to find this is Y, this is Z, and these are the three resistances. One is 8, one is 4, and one is 6. We are supposed to find the equivalent resistance. That is, if you combine these three together, what is the resistance you get between Y and Z? That is specifically asked in this particular question. Now, as I told you, I'm going to explain the series and parallel combination a little bit, right? So let's say we are discussing series combination. Two resistors connected in series. It can be resistors, it can be lamps, any electrical component connected in series, basically. Okay, and we have a power source or a battery. What does a battery do? It is a source of potential difference. See, current will flow when there is a potential difference. Not just that, you may have potential difference between 2 points, but current will not flow. Why? Because you have to attach those 2 points through a wire or a conductor, right? So you may have a potential difference which exists, but current will still not flow because the circuit is not complete. Okay, so a very tiny point, but a crucial one. Anyways, so we have, let's say, total voltage or potential difference of V. And let's say the circuit is complete. This is resistance R1, this is resistance R2. Potential difference between this and this will also be V, because that's the potential difference between these two. Same wire, so we have A and B. That's the potential difference between A and B. However, when we talk about R1, what will happen? There will be a potential drop across R1 because R1 will use up some of the energy, right? Electrical energy. R1 is an electrical component which will have its own resistance. So it will use up some of the electrical energy, let's say. That voltage drop is named as V1. Remaining will be used up by R2, which is called V2. So there will be two voltage drops, V1 and V2. The total potential difference cannot exceed the sum of the two. So V would be equal to V1 plus V2. That's the case of potential difference in series circuit. That means potential difference does not stay same in series circuit. As you see, R1 will have a different potential difference across it. R2 will have a different potential difference across it. It is a little difficult to understand series circuit from a potential difference point of view. Let's try to understand it with a current point of view. How does, obviously, if potential difference changes, then current will be same, right? Let's see how that works. Look at the direction of the current. It will be always from the positive towards the negative. Now look at the current, how it is flowing. Let's name it I. Current is flowing throughout the circuit. The wire is not changed. It's the same wire, no junctions. Junctions mean when you have 2 or 3 wires connected together. That's not there in the circuit, right? In a series circuit, it's like the same wire going throughout in the circuit. So current will flow through that wire and therefore current will be same. That's the reason, or that's an easy trick to remember that current remains same in a series circuit, right? And then you have that derivation of Ohm's law where V is equal to IR. You can just plug in the values and you'll get that the resistance in series, the equivalent resistance of series is actually R1 plus R2. Okay, I'm not going into the derivation of that because it's something which we may do later on. Therefore, if we go back to this question, we have 8 and we have 4, right? So 8 plus 4 will give us 12 ohms, right? That will be the series circuit resistance. Equivalent resistance between 8 and 4. Coming to the parallel combination. Parallel combination means when you have one resistor connected like this, another one also connected like this, and here you have the battery, the same potential difference source. So now between A and B, the potential difference is still V. And look, if this is V and this is 0, then over here also you have V and over here also you have 0. Over here you have V, over here also you have 0. So the potential difference is always V between any of these resistors R1, R2, right? So therefore, what do we see? When the resistors are connected in parallel, the potential difference is same throughout. So therefore, potential difference is same in a parallel circuit and current changes. So, and another point over here is, let's say current I comes out of it. So see, there is a junction over here. Current I will, some of the current will go into R2, some of the current will go into R1. The total current will be I1 plus I2 of this whole parallel circuit. So potential difference is same in series circuit, potential difference is same in the parallel circuit, and current is same in the series circuit, right? Let's apply this concept. So we already got the equivalent resistance for 8 and 4. We got it as 12. Let's put it down over there. So 8 and 4 is 12 ohms, right? And then we have a 6 ohm connected to this 12, right? And it is connected in parallel. We are supposed to find the combined resistance. So therefore, what do? 12 and 6, right? Okay, now I'm going to erase all the work over here because we are going to write on the paper, right? This is what you're going to write on the exam paper as well. So for 8 plus 4 will give you 12 ohm in series circuit. Okay, you don't write CKT, you write circuit, the whole thing. So this is 12. You can draw a small diagram on the side. That's fine. And this is your Y and Z, right? So the resistance across YZ is 12, right? Okay. And now we are going to discuss what our final answer would be, right? Okay. So we have 12 and 6, both are connected in parallel. So let's work out 1 by 12. So the parallel circuit resistance are given like this. 1 by R1 plus 1 by R2 is equal to 1 by R equivalent. So 1 by 12 plus 1 by 6 would be 1 by R. Take the common denominator, it's 12. So this will be 1 plus 6 into 2, which will be 2. So this will be 3 by 12 will be 1 by R. So R should be 12 by 3 or 4 ohms between Y and Z. Let me see if that is the answer with the mark scheme as well. Yes, so it is 4 ohms. 12 ohms is just for the series circuit and not for the whole thing. So your answer over here would be 4 ohms. And this is 4 mark. I hope this was clear. Quick recap. So 8 and 4 are connected in series, therefore you get a 12. 12 and 6 are connected in parallel, so you use this formula of parallel circuit. How do you get that formula? You can check back using Ohm's law and parallel circuit, all the definitions which we did today, all the formulae, not formulae, all the theory which we learned. From there you can derive this. It's easy enough. And that's how we get a 4 ohm. Okay. Next, calculate the potential difference across 8 ohm resistor. Let's have a look at the 8 ohm resistor. Now remember, 8 and 4 together are connected in series, right? And the potential difference is 24 volts. That means 24 volts is across 8 and 4 together, right? So let's start from there. You have 24 volts and that's the total potential difference across 8 and 4, which is just 12 ohms. So what is the current flowing through this arm of the circuit? How do we do that? Using Ohm's law, you can calculate this. IR is equal to V. So I would be 24 by 12, which is 2 amperes will be flowing through 8 ohm as well as 4 ohm. If 2 amperes is flowing through each of 8 ohm and 4 ohm, then you again use the Ohm's law, which is 2 into 8 will be your potential difference across the 8 ohm. That will be 16 volts in this case. I hope this made sense. If you have any questions, please post those questions in the comments. I hope you liked this video. Please don't forget to hit like and subscribe to my channel. Thank you.